Have you ever wondered how a wild scientific idea actually becomes a proven fact? Well, it all starts with having the right tools for the job. So today, we're going to pry open the physicist's toolbox. We're going on a journey to see how scientists measure, manipulate, and literally build our world, from things we can hold in our hands all the way to the invisible forces that shape our entire reality.
So that's the big question, right? This is what pushes science beyond your everyday rulers and kitchen scales. It takes us into this world of unbelievable precision and, honestly, some really clever thinking. I mean, how do you measure something you can't even see, or build a machine that can perform math? Well, let's find out.
We're going to explore our toolbox by opening up 4 different drawers, so to speak. We'll start with the absolute fundamentals, how to measure the physical world with pinpoint accuracy. Then, we'll dive into the invisible stuff, decoding light and sound and harnessing the power of heat. And finally, we'll put it all together to get a handle on the electronic building blocks of pretty much all modern technology.
Okay, let's open that first drawer, precision. Before you can even think about launching a rocket or building a microchip, you have to master the art of measurement. This is all about seeing the world with an accuracy that goes way, way beyond a simple ruler.
You know, for a physicist, close enough is basically a 4-letter word. It's just not good enough. Whether you're engineering a new material or testing a groundbreaking theory, absolutely everything depends on getting the numbers exactly right. And that requires specialized tools designed for one thing and one thing only: precision. So think about it for a second. How would you actually measure the thickness of a single coin? Your standard ruler, the markings on it are thicker than the measurement you're trying to take. You might get close, but you won't get a precise, repeatable number. And that is exactly why physicists needed to invent something much, much better. And here they are, the vernier caliper and the screw gauge. They might look kind of similar, but they're specialists with very different jobs. The vernier caliper is your go-to for general precision work, like measuring the diameter of a pipe. But for something incredibly thin, like a sheet of paper or, our coin, you need the even finer touch of the screw gauge.
So what's the magic behind them? Well, it all comes down to this concept called least count. This is the absolute smallest measurement any tool can possibly make. Before a physicist even starts an experiment, they calculate this value. It's the secret sauce that separates a wild guess from a true scientific measurement.
Okay, now that we've got a handle on measuring physical stuff, let's move into a trickier area. Things we can't always see or hold, like light and sound. The tools in this drawer are less mechanical and more about finding clever ways to reveal this whole invisible world of waves all around us. Just think, the light coming from your screen right now, the sound of my voice, it's all waves. And all waves have these key properties. 2 of the most important are wavelength, that's represented by the Greek letter lambda, and frequency. The next set of tools are all about figuring out how to measure these invisible properties. So how in the world do you measure the color of light? It sounds kind of impossible, right? But physicists have this incredibly clever trick. They use something called a diffraction grating. It's basically a tiny slide with thousands of microscopic slits carved into it. When you shine a laser through it, the light spreads out into a really predictable pattern. By just measuring the angles of that pattern and plugging them into a formula, you can calculate the light's exact wavelength. It's a perfect example of measuring the unmeasurable. And what about sound? Well, this table shows data from an experiment using a Helmholtz resonator, which is, just a fancy name for the physics of blowing across the top of a bottle. But look at the relationship here. As the volume of air inside the container goes up, the frequency, which is the pitch of the sound, goes down. By plotting this data, a physicist can predict the exact note for any size bottle. Okay, time for the 3rd drawer in our toolbox. We're moving from waves into another invisible but incredibly powerful domain: energy, specifically heat and electricity. Now we're not just measuring things anymore, we're starting to understand the fundamental laws that govern power itself.
Now, this sounds really complicated, but the core idea is actually pretty simple and kind of profound. Every hot object radiates energy. A toaster, a light bulb, even a distant star. The Stefan-Boltzmann law is the rule book that tells us exactly how much energy gets released based on an object's temperature. And you see that 4th power bit? That's huge. It means if you double an object's temperature, you don't just get double the energy, you get 16 times the energy.
And here's what that law looks like in its mathematical form. P is the power being radiated, T is the temperature, and that little squiggly sigma is a special number called Stefan's constant. This one
elegant little equation is what lets a physicist connect the temperature of a glowing light bulb filament to the amount of electricity it's pulling from the wall.
This next one is all about efficiency. So imagine you've got a stereo amplifier and a speaker. To get the absolute loudest, clearest sound without just wasting a bunch of energy as heat, the electrical resistance of the speaker has to perfectly match the resistance of the amplifier. This theorem is the golden rule that engineers use to design efficient systems pretty much everywhere.
Now, let's look at how these principles come to life in a real-world component. This is a thermistor. It's a clever little sensor whose electrical resistance changes a lot depending on its temperature. This is the practical application of everything we just talked about. It's the tiny, unsung hero inside your digital thermometer and in the safety circuits that keep your laptop from overheating.
All right, let's open our final drawer. This is where everything we've talked about really starts to come together. We're looking at the true building blocks of our modern world, integrated circuits, and specifically the king of them all, the operational amplifier, or as everyone calls it, the OAmp.
This humble-looking little chip, the IC741, is one of the most versatile electronic components ever made. But to use it, you first have to understand its map, the pinout. Each one of those little metal legs has a very specific job, from power to inputs to outputs. Knowing this map is the first step to unlocking all its power.
The real magic of the OAmp is that it's like an electronic chameleon. You can wire it up in different ways to do completely different jobs. The two most basic setups are the inverting amplifier, which makes a signal bigger but also flips it upside down, and the non-inverting amplifier, which just makes it bigger. Thankfully, the names in electronics are often wonderfully literal.
But it gets so much cooler. You can actually configure an op-amp to do math for you. An integrator circuit essentially adds up the input signal over time. A great way to think about it is like a smart energy meter. The longer your AC is on or the higher you crank it, the more the output voltage climbs, showing you the total energy you've used.
And then there's the differentiator, which does the exact opposite. It couldn't care less about the total signal, it only cares about how fast that signal is changing right now. So if the input signal shoots up quickly, the output spikes. If the input is just sitting there, steady, the output is zero. It's basically a motion detector for electrical signals.
And finally, physicists have this just beautiful way to see all of this in action. If you feed two wave signals, one that you know and one that you don't, into an oscilloscope, you can create these mesmerizing shapes called Lissajous patterns. The shape tells you everything. You can figure out the frequency ratio just by counting the loops. A figure-8 pattern means your unknown signal is exactly twice the frequency of the one you know. It's a purely visual way to measure something invisible. And that really brings us to the core takeaway here. These four different areas, precision mechanics, the physics of waves, thermodynamics, and complex electronics, they aren't separate subjects at all. They are the four pillars of the experimental physicist's toolbox, and each one builds directly on the last. So, we've gone from the simple act of measuring a coin all the way to building a tiny circuit that can perform calculus. These are the fundamental tools and concepts that allow us to not just understand our world, but to actually build it. The next time you use your phone or see a medical scanner, what you're really seeing is this toolbox in action. Which leaves us with the real question: what will we build with it next?